Okay.
Right. Okay. All right. Oh, well, I mean, congratulations.
Okay. And then all of our materials are copyrighted, so if you'd like to share this in any type of lecture or conference setting, make sure to get our written permission first. Otherwise, feel free to share this information with your colleagues within the office. Okay, and here are today's learning objectives. So first, we'll be going over the fundamental principles of coupled analysis. So this is something I mentioned briefly in our first presentation, our first lecture, and I'll be going into much more detail about it today. And I'll also be going over when to consider an advanced numerical approach for coupled analysis. So we'll also be touching upon the advantages of using numerical modeling and numerical programs for coupled analysis. And then part 2, we'll be going over approaches for seismic analysis and also sort of different methodologies or design approaches that exist for seismic analysis today. So this session is a little bit different from our previous sessions, wherein it's divided into two main parts. So the first part is a bit shorter, and we'll be going over just specifically coupled analysis. And then part 2, we'll be going over seismic analysis in detail. Okay, so as for part 1, these are just the main bullet points. I'll give you a basic introduction to the concepts and the fundamental principles of coupled analysis. I'll go over various types of coupled analysis that are out there. And then for the last two sort of sections, I'll go over numerical approaches as well as case studies or certain projects that have been done with coupled analysis. Okay, so first, what is coupled analysis? Essentially what it is when the output results of one analysis type are used in the input parameters of another analysis type. So to give further clarity, it's used for analysis types whose data is analytically interrelated. In other words, sort of the output for one analysis type depends on the results of a previous analysis. And what I'll do is I'll go into sort of greater detail about this, just through some specific examples. So why exactly is it needed? So projects that have analytically interrelated analyses need coupled analysis to be performed to ensure higher levels of accuracy. So in other words, there are certain projects in which that have analysis types that are interrelated. In order to gain fully accurate results, they can't be analyzed independently. They have to be sort of linked together through coupled analysis. Also, coupled analysis can contribute to designs that are more cost-effective while still meeting necessary design codes. So as you all know, the greater your accuracy is as far as your design parameters, the more effective you'll be able to design your projects or your structures, which in turn can lead to savings in cost as well as still meeting the necessary design codes. So here's the basic sort of procedure for a coupled analysis. So first, you have one analysis type and it's performed. Afterwards, the results from that analysis are imported into the input parameters of the second analysis. And then afterwards, the second analysis is performed while taking into consideration the calculations that were produced from the first analysis. So it's a fairly simple process. It's a three-step process, really. So let's go over a couple of examples. So here is an example of a seepage slope project. So as you can see, the title is sort of inherent. So it's the seepage slope coupled analysis. So seepage will be the first analysis that's performed, and then it'll be followed by a slope analysis. So here we have an embankment type project. As you can see, the reservoir is filled up to a certain point, a certain arbitrary point. But the main thing to consider here is that because the reservoir is full at this point, and because there's high water pressure at this side of the embankment, this will lead to extensive amounts of seepage going into the other side of your embankment, or the dry side. So as you can see, here's the phreatic line, or the seepage line. So as water pushes itself from a high water pressure to a low water pressure, this creates effective stress, or excuse me, this creates a poor water pressure, which affects the stability of this nearby slope, or the slope on the opposing side. So essentially what has to be done is, first and foremost, a seepage analysis has to be performed on this embankment, just to analyze the effective stress and as well as the flow quantities that are occurring because of this reservoir. Afterwards, after you have your pore pressure loads, in your next step, you would import the calculated pore water pressure loads into your slope stability analysis. So as you can see, here is sort of the completed project. And what I did was I took these results and I ran the analysis, one with the seepage taken into account and the other without it taken into account. So let's take a look first at the image on the left here. So as you can see, the pore water pressure loads were imported directly into our slope stability analysis, as well as the phreatic line, which is represented by the blue piece over here. And as you can see, the factor of safety is about 2.78, whereas in this example, pore water pressure loads are not taken into account, and thus a higher factor of safety was given. So as you can see, coupled analysis is particularly important in this type of project because without taking those pore water pressure loads into account, you would essentially be having an over-conservative design, which in turn could lead to an increase in cost, which might sort of put the stability of that slope in danger for future cases. Just to boil it down, with a coupled analysis, because our seepage results are taken into account, we're able to have a result that's more accurate as well as more safe. Okay, and here's another example of our coupled analysis. So this would be a seepage stress analysis. So essentially a seepage stress analysis is first a seepage analysis to analyze the effects of pore water pressure, followed by a stress analysis to analyze the effects of that pore water pressure. This time instead of a slope, it would be, in this case, an embankment, a retaining wall, a pile foundation, those sorts of structure types. So I'm sure you're all familiar with this equation. It's that the effective stress equals the normal stress minus the pore water pressure, and the pore water pressure is calculated just through this simple equation. The height of the soil as multiplied by the gamma of the soil. But essentially, that's very simple to sort of calculate with smaller scale type projects. But as you get into sort of larger scale projects with more complex geometry, coupled analysis becomes sort of more prevalent. It takes sort of a longer process to do, and that in turn makes numerical modeling more prevalent as well. So as you can see, just based on this image here, because the embankment or this tunnel lining is has water on both sides, there's large amounts of seepage happening here. So this would add increased pressure on these retaining walls as well as this floor of the embankment. So first, the seepage analysis is done to analyze this flow. Then afterwards, those pore water pressures are imported directly into your soil stress analysis, which in turn would help you to analyze not only your regular stress but your effective stress, which is most important because when you have a project such as this, when the embankment has water on both sides, ultimately, depending on the permeability of your soil and other factors, that could affect the stability of your retaining wall, and you would have to design accordingly. So as you can see, the effective stresses are clearly shown here, as well as an exaggerated deformation. So this is something that the engineer did just so that he could get a sort of a better view of how that retaining wall would deform and maybe sort of which points would be of most concern to him or her. Okay, and now let's talk about settlement slope analysis. So essentially, the first thing that we need to discuss is just the basic principles of settlement. So I'm sure you're all familiar with consolidation, but just as a recap, essentially what consolidation is when, for example, you have a clayey soil that's subjected to a certain amount of weight. Now, because the pores in clay soil are so small, water takes a long time to escape from those pores when weight is pressed upon it. So depending on how sort of resilient or how strong or how tightly compacted your clay is, this could take any number of days or even months. So as you can see, if you look to the right here, this is sort of an exploded view of your clay particles as well as the water. But as weight is pressed upon the clay, the water seeps out very slowly, and over time, that clay will begin to compact. So it'll proceed. Depending on the type of clay you have, you'll have certain amounts of settlement, as well as strengthening in the soil yourself. So that's another key thing to keep in mind, that when clay is consolidated, first and foremost it compacts, so there's displacement, and then second of all, the overall strength of it is increased as well. So because of these factors, that could affect certain analysis you may need to run for the structure itself, as well as, for example, maybe a slope stability type analysis, which we'll be discussing here. And then just as a quick side note before I continue, just keep in mind that consolidation is sort of a complex process. It can be done through spreadsheets, but it's more effectively done through numerical modeling because it has sort of more accurate results into account. It's also easier to sort of visualize it with numerical modeling. But the settlement itself is based on a logarithmic equation over time. I won't go into too much detail, but just keep in mind that because of this sort of level of complexity with consolidation, numerical modeling or a certain or a spreadsheet would be sort of your best bet, whereas doing hand calculations would take a exorbitant amount of time. Anyway, so for this type of analysis, first and foremost, you'd run your settlement analysis to see how the strength of your clay as well as the geometry of your project itself would change over time. And then afterwards, you would import those soil strength results and the updated geometry into your slope stability analysis. And then afterwards, sort of depending on the scope of your project, you would maybe adjust sort of the height of your embankment according to your needs. So for example, here the engineer took two different sort of cases. So the engineer, after he ran his settlement analysis, he was able to see that there was a certain amount of displacement that occurred. And what he did was he added 3 meters of additional embankment height and ran the slope stability analysis. And then he also did another case where he added 6 meters of embankment height and did the slope stability analysis, just so that he could see how that would affect his project, and then also just to see how much you could sort of account for as far as rises in water level and stability of the slope itself. But it's just important to keep in mind that in order for this analysis to run smoothly, and in order to get the best results possible, a coupled analysis was needed, where a settlement type analysis was done beforehand. And then afterwards, once the the new soil strength was calculated, as well as the displacement or the settlement of the soil, then afterwards he could get an accurate slope stability analysis that he could use for his final design. Okay, so now I'll go into numerical approaches for coupled analysis. So one of the main sort of advantages of numerical modeling is that it streamlines the work process. So look to the left here. As you can see, this is just a sample seepage stress type analysis. So there's the engineer here. He did the analysis of the seepage for this sort of area above the tunnel, and then afterwards he imported his results directly into an analysis for the effective stress. So for example, if you were to do this type of coupled analysis by hand or by spreadsheet, it would take sort of a much longer amount of time, because you can't really sort of interlock the analyses as seamlessly as you could through a numerical modeling program. So for those of you who are familiar with SoilWorks minus GTS, you should be, if you had any coupled analysis, you should be familiar with this process. It's very straightforward and it's very efficient, and something that can save you a lot of time and effort in the long run. And the same principle applies to seepage analysis. So here we have another sort of similar embankment type problem. So here, because there's water on this side of the embankment, the head is maximum at this side, and then it's minimum at this side, and then you'll experience a significant amount of seepage on this side of the embankment. So what you would do is you would, using the program, you would run your seepage analysis, you get your pore water pressure loads, and then you could just import them directly into your slope stability analysis. So you wouldn't even have to change your model file. Whereas if you had a spreadsheet, if you're doing them by hand, you'd sort of have to go from one analysis to another, and you could lose, depending on the sort of scope or the size of your project, you could lose a significant amount of time, or you'd have to invest a significant amount of effort just into doing that transition. Whereas if you have the numerical modeling program, everything is much more seamless. So as you can see, this is sort of just a screenshot of the engineer importing the loads directly into the slope stability analysis. And here we ran a limit equilibrium method slope stability analysis along with a strength reduction method analysis, which is sort of a finite element analysis. So those are just the basic principles of coupled analysis. So just as a review, just keep in mind that coupled analysis is just, and let me go back to where we began here before I give you the quiz. So coupled analysis is used for analysis types whose analyses are interrelated or analytically interrelated. So you need one analysis to be performed before you can successfully or accurately run the other. Okay, so I think that's a pretty straightforward principle. Once again, if you guys have any questions about this later on, feel free to contact me. Once again, I'll give my email address. You all should be sort of familiar with me by now, I hope. But anyway, let's just do a quick case study, and then I'll give you guys our first quiz. So here's the Inje Tunnel in South Korea. So for those of you who attended session 3, you should be sort of familiar with this project. I shared it in that presentation as well. But the reason is I decided to share it again was because it's a very sort of powerful example of how coupled analysis can be critical for certain types of projects. So here we have a tunnel that's built below the Bangtae Creek. It's about 132 meters below. And this creek, depending on the season, would have various sort of water levels. So what the engineers did was they calculated the effects of seepage for a sort of maximum water level or a high rainy season. And then just using their finite modeling, they were able to analyze the seepage and to get the pore pressure loads acting directly on the tunnel lining. Once those pore water pressure loads were modeled onto the tunnel lining itself, then they were able to analyze, or excuse me, to design the tunnel effectively so that it would be able to be sort of resilient to a maximum or a critical condition as far as seepage. So here, in this particular example, a coupled analysis was absolutely necessary just to ensure that they had this very important variable to take into account. So as I'm sure you've noticed, seepage analysis, or excuse me, coupled analysis is typically used with in tandem with seepage and another analysis type because pore water pressure can have a very sort of strong, sort of critical effect on your project. So pore water pressure loads would have to be calculated through a separate analysis, through seepage analysis, and then those results would be imported into your subsequent or your following analysis type. Okay. So now it's time for just our first quiz. It follows the same a little bit early. So moving on. So now we're on to part 2, which will be specifically on seismic analysis. So here I'll just go over the very fundamental or the basic principles of seismic analysis, numerical approaches for it, as well as a case study. So first, why is seismic analysis needed? First and foremost, it's a major aspect of structural analysis for high seismic regions, regions such as California, Hawaii, Alaska, etc. So seismic loading patterns are highly concentrated and cyclical, which means they sort of vary depending on time. Therefore, they cannot be analyzed with numerical approaches used for typical live loads. So the main sort of concept to get from that is that numerical modeling, or excuse me, that seismic analysis is very sort of unique, and it requires sort of a very sort of special set of calculations in order to effectively consider it in your design, and we'll be going over those methodologies shortly. So why numerical modeling is needed specifically for seismic analysis? So even the simplest seismic analysis methods require the consideration of the extensive amounts of variables. So as I said, because seismic analysis is time dependent, it's cyclical, and it varies very sharply over a very short period of time. A large number of variables needs to be considered in order to account for that. So that's why numerical modeling especially becomes more effective for it, because it can take all those variables and it can run the calculations much more efficiently than made possible by hand in spreadsheets. As you can see, calculation processes are very time-consuming and repetitive when done by hand or by spreadsheet. So essentially, numerical modeling would help you to cut out a lot of sort of legwork as far as seismic analysis. And then last and not least, finite element analysis or finite element modeling allows for more accurate and efficient modeling, especially for larger scale projects that require advanced seismic analysis methods. So we'll be going over several different sort of analysis methods, but just keep in mind that for larger scale projects, projects that are in high seismic zones that are sort of larger scale, that have more variables to be taken into account, they require a very high level of seismic analysis, which can only be realistically be done through a numerical modeling program. Okay, so before I go too much into detail just about seismic analysis itself, first let's talk about the principle of plate tectonics. So why exactly earthquakes happen? So plate tectonics is just a very basic or sort of straightforward concept, and basically what it means is that the Earth, as far as the Earth's surface, consists of several large masses of plates that are sort of separated here. So as you can see, those top plates are called the lithosphere. Okay, so that's sort of the top part of the part that's just below the crust. So there's the soil layer that we work in as geotechnical engineers, a continental crust. But below that layer, there's the lithosphere, which is very hard. It's a very sort of hard rock region. And once again, keep in mind that the Earth's surface is made up of several of these sort of large plates. And below the lithosphere, there's a level called the asthenosphere, which is essentially sort of a liquid magma or a viscous type material. It's very hot, and what happens is the lithosphere, which is solid, slides along the asthenosphere. And because these large plates of the lithosphere are sort of sliding very slowly against each other, that leads to a lot of sort of seismic regions in particular parts of the world. So let's move. So here we have a breakdown of just of the different plates that consist of the Earth's surface. So I won't go through just all the names of the plates, but just keep in mind that high seismic regions correspond directly to where the plates sort of meet against each other. So these arrows represent the direction the plates are drifting towards. So for those of you who took maybe geology courses, back in high school or back in college, you'll realize, or you'll maybe remember a concept called continental drift. Essentially, what's happening is all these plates are moving very slowly along the asthenosphere. Um, it's slowly to the point where, for example, the coast of California, they say it moves maybe an inch or so per year. But as you can see, that adds up over time. So as you can see, the African continent, the North American continent, the South American plates, essentially, millions of years ago, they were all just one large continent. But over time, as these plates sort of drifted away from each other, these separate continents were created. So plate tectonics is related directly to a concept called continental drift. But anyway, to go back to seismic analysis, as you can see, high seismic regions, correspond directly to areas where plates collide. So, for example, here in California, the reason there's so many earthquakes in that particular region is because it's right near a fault line where these two plates are sort of grinding up against each other. Whereas in New York, or for example, just the Northeast in general, it's located in an area that's relatively far away from any sort of any borders of plates that are sort of colliding or merging. So as you can see, depending on where you are, sort of on, well, let's just focus on America. So let's go to the next slide here. So just keep in mind that the plate or the fault line resides right here, just along the coast of Mexico and California, as well as Alaska and Canada. So if you go down here, as you can see, because it's right by that fault line, the sort of hazard for earthquakes increases dramatically along this area, whereas parts along, sort of the west or the Midwest are relatively safe. So depending on your geographic region, as I'm sure that you engineers from California are well aware of this, that seismic analysis is extremely important, especially for regions in Southern California that are right along the coast. You have various landslides that take place. Earthquakes can be sort of a seasonal occurrence, whereas in New York or the Midwest, the seismic analysis calculations or methodologies that you use, they're still in there, but they're not as prevalent. It's sort of it's not a major part of your calculations. So that's just one of the main things to keep in mind, is that depending on your seismic region or the area in which you work, seismic analysis becomes sort of more prevalent as you go further out west. And as you reach the Midwest or the Northeast even, seismic analysis, it's still something that's done, but it's not taken into that much consideration because there's sort of less risk there. Okay, so now let's get into just the calculations of seismic analysis itself. So first let's talk about 1D ground response analysis. So essentially 1D ground response analysis is the analysis of how soil responds to cyclic loading or seismic loading. So as you can see, as I mentioned before, seismic loading is very cyclic. So here we have a time history graph. So as you can see, in a matter of seconds, the function goes up and down, dozens of times. So this is just a measure of the acceleration or the seismic acceleration versus the time. So as you can see, within just maybe half a minute, you see some very high changes in the loading as cyclically. So as you can imagine, when this loading is being applied to the surface of a building, this can lead to a very sort of unique situation where simple static or live loads wouldn't be able to sort of account for this type of behavior. So the dynamic behavior of soils is quite complex and fairly unpredictable as well, because no earthquake or no two earthquakes are exactly the same. So they require very complex models which characterize the important aspects of cyclic behavior. So sort of this back and forth motion, sort of this, within a couple of seconds, there'll be negative and positive forces being acted upon this foundation within a very short period of time. And then dynamic strength of soil during an earthquake generally differs from its static strengths, since the effects of strain rate and cyclic loading gets added as well. So just keep that in mind as well, that the way a soil sort of reacts to seismic loading is very unique, and static and typical live loads wouldn't be able to account for that. Okay, so for those of you who attended session 1, this table should be fairly familiar. This is just sort of a chart that denotes the various sort of criteria that we have to take into account for seismic analysis. So things such as dimension and domain. You have various categories for them, and they have, as far as the application to design, dimension is a function of 1D ground response analysis, which we'll discuss shortly. As well as the stress-strain relationships. So this is also very important. So I'm sure you all remember the differences between linear and nonlinear behavior in soil. So typically soil, it behaves in a nonlinear fashion. So this is very important to take into account when you're doing your seismic analysis. And we'll go into both linear and equivalent linear sort of analysis processes for soil as they relate to seismic analysis or seismic loading. And then also pore water pressure is also very, very important. So depending on the type of analysis you run, so for example, if you were to run an analysis for how soil responds to a seismic loading when it's drained versus undrained, the results would be very different. So for example, when soil is undrained and seismic loading is applied to it, that soil will actually behave as a liquid in a phenomenon called liquefaction. So we won't be going into too much detail, or we won't be actually going into detail very much at all about liquefaction, because that's sort of a deeper sort of concept that would require its own presentation. But just keep that in mind, that when you have undrained soil conditions and seismic loading is applied to it, that creates a very sort of dangerous and unpredictable environment for your structure. But for now, we'll just keep it simple, and we'll focus mainly on drained analysis. So the analysis procedures that we'll discuss will assume that the soil is drained, so without groundwater. Okay, so first we'll go into two main soil models that are used for seismic analysis. The first is equivalent linear, and I'll go into greater detail about it in the subsequent slide. But first and foremost, I just want to go over its main advantages. So just keep in mind that equivalent linear analysis is the simpler and more efficient soil model. So it's computationally efficient, which means you can easily do it just through a computer program. It's heavily tested. It's very widely used because it's so simple, and a variety of different codes are available for it. So for those of you who have done equivalent linear analysis before, or just basic seismic analysis, this should all just be reviewed for you. It's a very sort of straightforward model. It's very simple to use, and it's enforced by a lot of codes. However, it does have several disadvantages. First and foremost, it's not appropriate for very soft soil profiles, so it can account for deformation, and then it can't account for cracking or failure. With equivalent linear analysis, you're assuming that the soil won't deform or won't have any significant failure. Also, there's significant artificial amplification near fundamental methods. So for example, I'll go and I'll show you sort of a time history graph later on, but the main sort of point to get across is that with the equivalent linear analysis, you're making several assumptions, which, depending on the scope of your project, may or may not have a negative effect upon it. But just keep in mind that equivalent linear analysis is used for simpler, more straightforward projects, and sort of maybe like low seismic zones. So these sort of assumptions wouldn't harm your project, whereas sort of more complex projects and higher seismic zones, you'd have to use a more complex model, which is the cyclic linear model. So just before I continue, there's potential de-amplification at other periods, so that's just another way to say that there's certain assumptions made as far as your time history graph. And then it can't do effective stress methods, so it can't take undrained conditions into account. Okay, so cyclic linear models. So the main advantage of cyclic nonlinear behavior, or excuse me, cyclic nonlinear models, is that stress-strain behavior is more realistically modeled. So it can be formulated in terms of effective stress, so it can be used for undrained conditions. And it can model deformation as well as response. So that's another sort of key factor, is that it can take deformation of soil into account as well as failure. And it's under active development. So that's one of the key sort of advantages of it, is that there's still people or engineers, or excuse me, scientists who are working on developing cyclic nonlinear analysis to be more widely used, or to be more efficiently used. So the disadvantages of cyclic linear modeling is it requires advanced constitutive relations. So in other words, it takes more variables into account, and because these variables are needed for cyclic nonlinear analysis, sometimes it can take longer to develop the constitutive models, or to find those variables. Modeling parameters are not well established, so because it's under active development, certain parameters that are out there and available to you, they still need sort of I mean, there's still sort of a larger margin of error than would be in equivalent linear analysis, where the tests are sort of more sort of stabilized. And then also it requires advanced laboratory testing. So, for example, if you were to do a seismic analysis for a certain site, you might have to run your own laboratory test, or you might have to sort of sublet that work to someone else in order to get these constitutive models that you would need to perform your cyclic nonlinear analysis. Okay, so let's take a look just as an example of a nonlinear an equivalent linear model. So here we have a time hysteresis loop. So essentially what's happening here is the the shear amplitude is being modeled against the strain, the stress amplitude is being modeled against the strain amplitude. And because the loading itself is cyclic, just imagine the soil going from one value to another. So it's sort of going back and forth as the earthquake is going. So this is essentially the pattern that you're assuming the soil to take, or the stress strain pattern that you're assuming the soil to take as as it's being seismically loaded. Now, obviously, because soil is nonlinear, this isn't an exact sort of replica of how it would behave, but this is just an assumption that you're making just for the sake of simplicity. So certain things to take into account. So the main important properties of the loop are its inclination and its width. So the more inclined this loop is, sort of the greater strain, the greater stress, the greater strain. So for example, if this loop was more inclined, say tilted this way, it would sort of handle greater strain with less amounts of stress. Whereas if you would incline it this way, the behavior would obviously be converse. And then also the damping ratio is dependent upon sort of the area of the loop. So I'll go into more detail about damping ratios, but just keep in mind that your damping ratio, the parameter that you input for your seismic loading, or for the soil parameters for your seismic loading, are directly related to a model such as this. So before I move forward, let's talk a little bit about damping ratios and why that's important. Okay, so here's sort of a more detailed or more accurate sort of view of how soil behaves under cyclic loading. But as mentioned before, let me see if I can get it. Okay, so damping is calculated from delta W, which is the area of the hysteresis loop itself, and the area of the triangle. So once again, depending upon how your loop is oriented, as well as the width of it, that would sort of determine your damping ratio. So what exactly is damping? Damping ratio is a measure of how much a system will oscillate before returning to equilibrium. So just imagine, if you will, sort of a piece of soil that's being seismically loaded, that's experiencing an earthquake. Depending on how stiff or how rigid that soil is, after the earthquake is done, it'll shake a little bit, and then it'll return to its sort of steady state or its normal state. So think of it this way: when their damping ratio is over 1, the system returns to equilibrium without oscillation. So just imagine a very solid rock being subjected to seismic loading. Once that earthquake is done, that rock will just be still. There won't be any sort of vibrations within the system itself. Whereas if you have a system that's underdamped, so a ratio that's 0 or very near 0, the system oscillates very frequently. So just imagine just maybe a plate of Jell-O, and say you shake the plate, and then afterwards, after you take your hand away, the Jell-O will still shake for a few seconds before returning to equilibrium. So that's sort of the main difference to take into account, is that the higher your damping ratio is, the more resilient or the more stiff your soil will behave when seismic loading is applied to it. Whereas if it's closer to 0, the more it'll give way to seismic oscillations even after the earthquake is gone. And once again, I won't go into too much detail just about the loop itself, but just keep in mind that your damping ratio is directly related to a model such as this. Okay, so now let's talk about cyclic nonlinear models. So as I mentioned before, cyclic nonlinear models are more detailed, and they take more variables into account, therefore they're more accurate. However, the trade-off is that they take more time to create, or they take more time to get all the parameters. So let's take a look. So the main difference between the hysteresis loop for the nonlinear model and the linear model has to do with the number of amplifications it does. So here, this outside loop seems very familiar because it's related directly to your equivalent linear model. But the main difference is that the cyclic nonlinear model takes this loop into account as well as several other amplitude loops. So for example, for the first second of your seismic loading, your soil your stress, or excuse me, your stress strain behavior will be something like this. But in the second loop, say for example the soil becomes sort of more compact or more loose, depending upon which you can either get a loop on the outside or the inside. But with this soil, obviously it's getting sort of more compacted, it's tightening up, so the loop tightens and gets smaller for the second cycle, and then it gets smaller again for the third cycle, and then smaller again for the fourth cycle. So this is a more realistic prediction or calculation of how your soil would respond to seismic loading. And then afterwards, the program, or excuse me, not the program, your nonlinear model, you would just take the tips of all your amplitudes or the critical points, and you would link them together in a curve such as this. So this is called the backbone curve. And then using your backbone curve, you'd be able to extrapolate certain points that more accurately measure how your soil would behave during certain points of the earthquake. So in other words, instead of, let me go back to the previous. So as you can see, with the equivalent linear model, what you do is you just take a tangent off maybe a certain point of one loop. So you have to make certain assumptions that, first and foremost, the assumption you would make is that the soil behaves the same way for each and every oscillation, which obviously isn't true, but for certain types of projects, you could make this assumption, assuming that this is a critical condition. Whereas in the, go back here, in the cyclic nonlinear model, you have an understanding that soil behavior changes with each sort of, as the earthquake progresses. So as you can see, instead of just having to use one loop, you have several loops that more accurately define how your soil would respond to that seismic loading. So you'd be able to extrapolate sort of various values of stress and strain depending on where you are on this loop, and they'd be far more accurate than the types you would have for your equivalent linear model. Okay, so just to review, I'm going to give you another quiz, but just the main thing to keep in mind is that cyclic nonlinear models are used for sort of higher end projects where you have more variables to take into account. So it's more accurate, but it's less efficient, whereas the equivalent linear model, you have several assumptions that you have to make, but it is more efficient computationally, and it's more widely used for sort of smaller scale projects or areas where seismic regions that are away from fault lines. And then just review of plate tectonics, just keep in mind that depending on where you sort of reside on the Earth's surface, if you're closer to a fault line, or in other words, where two plates meet, you're in a higher seismic zone, so earthquakes become more prevalent in that area. So that's just the basic review. So I'll pull up our second quiz, and once again, you'll have. Okay, perfect. So I see everyone was able to finish their quiz and submit it early. So I'll just close the quiz early now and move forward to our last and final section. So now that we've talked about sort of constitutive models or ground model for seismic loading, let's talk about the analysis that we use just for structural design as well as structure interaction design. So first, I'll talk about the most basic type of seismic analysis that's available, and it's called equivalent linear analysis. So that's, it's a good way, sort of a good way to remind yourself of these sort of different models. That equivalent linear sort of corresponds to your equivalent linear constitutive model for soil. So essentially, this is the most straightforward and simple seismic analysis type, and it's used typically for smaller scale projects in low seismic zones. So essentially, and also it's defined by your building code. So depending on sort of the region you're in, the code will be sort of enforced, and you can just follow sort of a step-by-step procedure on how to model your seismic loading. But essentially, what you're doing is you're assuming that the seismic loading follows a distributed loading pattern. So for example, here you have I don't know how many stories this is, but you have a low-rise building, and then in order to create your seismic loading, what you do is you just take a force and you model it as a triangular distributed load, which increases the higher you go up, because the farther away that you get from your foundation, sort of the more sort of flexure that you'll experience as you go higher up. But essentially, obviously you're making several very large assumptions when you're doing this type of analysis. But for smaller scale projects, in low seismic regions, for example, maybe out in the Midwest, or a region that's, sort of maybe the center of the United States where seismic vibrations are very low, an analysis like this would suffice. So that's just the first type of analysis that's available. And for those of you who might be working in sort of low seismic regions, this should be, very familiar, and you should be, very sort of well acquainted with it. But now for more complex or sort of higher end analysis, the first analysis type we'll talk about is response spectrum analysis. So first, it's required by many building codes except for very simple or very complex structures. So of the three and sort of analysis types that we'll talk about, the second one, response spectrum analysis, is the most widely used because, it's for very simple structures, you can just use the equivalent linear analysis. But for structures that might be in sort of higher seismic zones, the closer you get to out west, or maybe even in the north, here in New York in the Northeast, in this region, response spectrum analysis is used quite often because the seismic zone is still a little higher than the ones in sort of the Midwest or the Central America. So response spectrum analysis is very prevalent in those regions because even though the seismic loading isn't as high as it is, say, in California, there still needs to be taken into account to an extent where, a more detailed analysis is the one available in equivalent linear. So it's sort of the middle ground. So if you have a structure that's very simple in a low seismic region, you use equivalent linear analysis. But you have one that's sort of in the middle range. It's not a very complex structure in a very high risk region, but it's still, in a seismic region, and it's still a building, that isn't low-rise, that might be a little bigger, then you would use response spectrum analysis. It's sort of in the middle, and because of that, it's the most widely used. So it's useful when detailed time history records are not available. So I'll discuss more about time history records later on when we go over our final analysis type. But just keep in mind that for more complex or higher-end analysis, you'll need what's called a time history record or series of time history records, which very closely detail a series of sort of critical earthquakes in the area in which you're residing. So for example, if you're working in, I don't know, maybe say Los Angeles, a very high seismic region, if you were building a building there, you'd have a whole database of time history records available to you of critical earthquakes that happened over the years, and you would use those time history records in your analysis. So I'll go into greater detail about this later, but just keep in mind that with response spectrum analysis, you don't need these time history records. You can work without them. So that's particularly useful because using those time history records and implementing them is very sort of time-consuming. It's a very sort of detailed process. Also, keep in mind, response spectrum analysis utilizes multiple modes of response of a structure. So you probably, for those of you who are new to this concept, you're probably wondering, what this picture means. So essentially, with response spectrum analysis, is that you're saying that the structure will have several different mode shapes depending on the sort of the level of the earthquake or the level of seismic loading and the point at which it's at. So, for example, here the earthquake is, maybe it's just beginning, and the wave is less severe. So then you'd assume, or you'd give that assumption that that your structure, or say your beam in this example, would bend or would oscillate. Obviously, this is an exaggerated view, but this would essentially be the displacement curve it took. Whereas when the earthquake increased in frequency and in strength, then you'd have a second mode shape that you'd run calculations for, and you'd assume that the forces would act in such a way. So for example, you might have a node here, you'd have a force acting this way, and then you'd have a node here, and you'd have a force acting this way. Whereas in the first mode, you'd only have one force acting this way. And then finally, maybe you'd have a third node for maybe critical conditions when earthquake is at its strongest, and you have maybe three nodes this time with a force acting this way, and this way. So the purpose of these modes is to take sort of each situation into account. So as I said before, because seismic loading is cyclic, the forces acting on your structure will behave very differently. So it'll vary from second to second. So what you'll do is you'll take sort of three critical modes and sort of three critical conditions upon which the loads are acting upon your structure, and you'll perform the calculations for each one. So as you can imagine, the displacement for this one would be sort of completely opposite from this one. But both of these conditions are very realistic and very probable in the event of an earthquake. For example, if you're only designed for this mode or only designed for this mode, and you're to neglect these previous two, you'd essentially be designing your building to withstand one portion of the earthquake but not the other. So that's why taking all of these modes is very important, just to take into account sort of critical loading conditions for various points of the earthquake. Okay. So yeah, this is something I just discussed. So it assumes a response of multi-degree of freedom as a combination of multiple single degree of freedom systems. So essentially, you'd have these different sort of systems, and then you'd model your nodes and your forces according to your corresponding graphs or your corresponding seismic loading. Okay, so now let's talk about time history analysis. So the main thing to remember about time history analysis, it's higher-end seismic analysis, and it's performed when detailed evaluation is required or when a complex structure and ground conditions exist. So I mentioned analysis that's done in California, Washington, Alaska, Hawaii. Most engineers that I'm acquainted there, they typically deal in time history analysis for almost all of their projects, just because of the high seismic region that they're in, and also for larger scale projects that are built there. Time history analysis is their only realistic way to design for the seismic loading that takes place there. So it takes the most variables into account. So as I discussed before, you'll need access to a number of time history records, and these are standardized. For those of you who work in high seismic regions, I'm sure you're well aware of the time history records that are available in your area. So you need access to these records, and then also you'd have to import them into the calculation itself. So I won't go into a very high level of detail, because time history analysis, this in and of itself could be its own lecture, just how to go through it. But I just want to help you guys to become aware that time history analysis is especially useful for high loading or high seismic conditions. So it requires more time and effort to perform, obviously, and it requires time history graphs of path earthquakes in the area. And also here's the variables that are taken into account as far as your time history functions. So it takes into account the acceleration, or the seismic acceleration of your loading. It takes into account the forces, so the forces that are being applied to your structure, the moments, and as well as the displacements. And also, the closer the timing of the steps, the more accurate the solution will be. So for example, if you were to subdivide this this graph to get more results for a number of time steps. So if you were to increase this to, say, double, you'd have obviously a more detailed and more accurate analysis, although it would take obviously longer to run. So now let's talk about something called soil springs. So this is another key factor of time history analysis. So soil springs and time history functions are generated by the geotechnical engineer. So once you have your time history record, it would then be on you to create a time history function, as well as soil springs. So essentially what a soil spring is a very special element used in numerical modeling to simulate seismic loading and ground behavior to that seismic loading. So for example, as I said, just imagine, say for example, like a bed spring, or excuse me, a bed spring. So say you have a bed spring, pushed up against like a cinder block here, or a tube. If you were to apply a force to it, that spring would oscillate. So just try to imagine it that way. That's why they're called springs. So these spring elements take into account the oscillating behavior of how say for example you apply a seismic load to this pile foundation, it's going to shake back and forth. So these soil springs would take into account that type of behavior. And what you'd have to do is you'd have to create a soil spring for the tips, for the lateral, to account for lateral behavior, for torsional behavior, and vertical behavior. So as you can see, it's a long process that requires a lot of attention to detail to model all of these springs. And then each of these springs, depending on the soil layer, depending on the type of earthquake you're modeling, each would have its own time history function associated with it. So that's what makes time history analysis so cumbersome and yet so accurate, is because of this level of detail. With response spectrum analysis, obviously you have to make certain assumptions, but whereas with time history analysis, because these variables are taken into account, we have less assumptions as well, but it also requires a greater level of detail. So also, data can be generated using 1D analysis, ProShake. So ProShake is just a numerical modeling program specifically for seismic analysis, very prevalent in the West Coast. Midas GTS and Flush 2D. So as far as 2D and 3D analysis, these programs are both equipped to handle it. And then typical analysis, so you can use free field method for soil interaction. So that's just a method, like a calculation that's used to analyze the soil interaction during seismic analysis. So when your structure is in direct contact with the ground, there's going to be a very sort of unique type of behavior that can be sort of calculated or simulated using this analysis type. And then continuum analysis involves modeling both soil structure and the structure together. So once again, that's another sort of soil structure interaction analysis type that's available to you. So these are typically used for projects in which engineers want to sort of maybe do it by hand or have a closer attention to detail. Whereas engineers who are already sort of familiar with the process, they typically use just the numerical modeling programs to do sort of the extensive calculations for them. So typically a good way to sort of go about learning about seismic analysis is first to familiarize yourself with these two methods, and then later on, once you understand the principles or the governing principles behind them, then you can use ProShake and your numerical modeling programs just to sort of save you on time. But it's always sort of a good rule of thumb to understand the underlying principles. That way, when you're inputting your parameters for programs such as this, you understand what all those parameters mean and sort of the calculation process that's taking place. Okay, so let's talk a little bit more about soil springs. So as you can see, here we have another example of this is a sort of a 2D example of how soil springs are being applied to a drilled shaft. So as you can see, I assume that because the soil varies on these different levels, and also because of different positions of these nodes themselves, each of these soil springs has a different time history of function attached to it. So response spectrum is defined at the rock level rather than at the ground level as in response spectrum analysis method. And then forcing functions are defined at different levels varying with depth and soil properties. So once again, just keep in mind that you need such a wide sort of database of time history functions because of the different variations in soil behavior depending on where you're at. So if you have 5 different, or maybe 3 or 5 different soil layers, you'd have a time history function for each of those layers. And then soil springs are defined along the length of the foundation and correspond to the forcing function. So either the force displacement depending on the geotechnical analysis. So once again, the forcing function is sort of directly related to your time history analysis. So the main sort of purpose of these soil springs is essentially just to model the oscillations in your structure, as well as to model your seismic loading functions on them. So once again, these loading functions will, apply a different sort of seismic loading condition to each of these nodes and each of these springs, and therefore you'd be able to get, much more sort of detailed and accurate analysis. Okay, and then how time history data is created. So one, response spectrum at the rock level needs to be created. So that's, the very first step. So at the rock level, the engineers or scientists determine how that rock responds to your seismic loading. And afterwards, they find accelerations at rock level from, these various sort of agencies. So site-specific hazard analysis. So for example, if you're working within, any one of these regions here, there should be like a database of different sort of response spectrums for each of those areas. So, depending on your area, you just have to go to these various agencies to find the response spectrum that applies to your particular region. And then last, you'd pick an existing acceleration time histories that match the target response spectrum for the project location. So essentially you'd have all these time history graphs available to you, and then you just have to sort of pick and choose. And once again, this is where it really is up to the engineer to decide which acceleration functions, which time history functions are best suited for their project. So I won't go into the details of how that decision is made, but just keep in mind that this is really where the engineer's expertise comes into play, because there's no sort of set guideline that tells you, okay, use this one, use this function over that function. It's really sort of dependent on various factors, the scope of your project, where exactly it's located, how large your project is, etc. But essentially, it's really up to the engineer to find that database and choose specifically which time history function matches the needs of their project. But that's just a brief overview of how these, how this time history data is created. So it's essentially scientists who have recorded all these different responses of responses of soil to seismic loading. So that way, engineers that have these resources available to them when they do their seismic designs. Okay, so now let's take a direct analysis or direct comparison of time history analysis versus response spectrum analysis for a bridge foundation project. So this study was performed by Benjamin Szymanski from Parsons-Bergerhoff. So he's a bridge engineer, but he decided to just do a study of how response spectrum analysis and time history analysis sort of differ as far as the results are concerned in his particular bridge project. So here it was just a hammerhead pier, 7-foot columns, and it was supported on 8-foot drill shafts. So here's just a sample of one of the time history functions that he used for his time history analysis. And here's an example of one of the response spectrum functions that he used for his response spectrum analysis. So as you can see already, the time history function, you can tell it's going to be a lot more detailed, a lot more specific, because of the range of variables that are available to you. Whereas with the response spectrum analysis, the function is much more simple and much more straightforward. So let's take a look. So ultimately, here are the final results of his experiment. So here are the results of the response spectrum analysis. So just for a moment, for I believe one of the pile foundations, it was within this range in the M, in the Y direction, and the Z direction. Whereas with time history analysis, as you can see, the moment was considerably less, by about 56% for moment in the Y direction and 42% with moment in the Z direction. Okay, so what exactly does this mean? So response spectrum analysis essentially gave you a very conservative result. Because less variables are taken into account, the analysis itself has to be conservative in order to be realistically used in the field. So as you can see with the time history analysis, because it had more variables to take into account, because it was more thorough, it gave this particular engineer moments that were far less. So using these results, he would be able to create a more optimized design. So in other words, if you have if you use your time history analysis, then you can, say with great confidence that because of, these calculations, because of what the simulation that I just ran, these will be sort of the critical moments. You'd be able to have a design that's more optimized, that's more cost effective. So ultimately, with using the time history analysis, you'd be able to have maybe bids that were more competitive, depending on, your project, because depending on your project, a calculation difference such as this would help you to create a design that could save maybe, thousands of dollars even. But it really depends on the project itself. But just keep that in mind that with response spectrum analysis, although it's easier to run, it is more conservative. Whereas with time history analysis, it takes longer to run. I'm sorry. I see that someone can't hear me, so just give me a second here and I'll adjust the audio. Okay, so I turned up the volume in my microphone. So if you still can't hear me, let me see. Okay, yeah, sorry about that. One of my okay, that's clear. Okay, so sorry about that. There's a little bit of feedback there. So I'll just review over just that quick point that I made. So essentially, with response spectrum analysis, the results will be more conservative because you're taking more assumptions and you're making more assumptions and you're taking less variables into account. Whereas with time history analysis, it takes longer to do because obviously, the sort of the level of analysis is higher. There are more variables taken into account. It's less conservative and it's more optimized. So there's that trade-off. So it really depends, once again, on the type of region you're working in as well as the scope of your project, which type of analysis you would run. But just keep that principle in mind. So now this isn't always typical. Just keep in mind this is, just one experiment. This is one case study. So once again, as Benjamin made sure to point out, it really depends on the structure type, the structure height and length, soil properties, and various other factors. But one of the main things just to remember about time history analysis is that it's used for sort of higher level projects, and it's used for projects that reside in very high sort of seismic zones. Okay. So now we'll just go over, once again, just the pros and cons of time history analysis versus response spectrum analysis, just a summary of what we went over. So the pros of time history analysis. So in some cases, it's possible to reduce the level of steel reinforcements and possibly concrete. So that would require revising analysis. So once again, that's just another way to say that with time history analysis, you can create designs that are more optimal because you have results that are more realistic and less conservative. Also, it can amount to a considerable cost savings by reducing substructure quantities. So in other words, so the substructure is just another word for, so this, this engineer was a bridge engineer. So in reducing the size of those substructures like the bridge piers and, parts that are, supporting the bridge, they can cut costs of the project while still maintaining safety. Okay, now let's talk about some of the cons of time history analysis. So it's not applicable and it's insignificant for conventional type projects. So for example, if you were, I don't know, working on maybe just a regular building in the Midwest, time history analysis wouldn't be very realistically for it to run. It'd be too much of a time investment, and you'd be able to achieve results that are, completely acceptable with response spectrum analysis. And then it's time consuming and requires a significant amount of computing power to handle all of the data. So that's where sort of numerical modeling programs come into account. So even though you can save a lot of time with numerical modeling programs, time history analysis in and of itself is still a very lengthy process. So if you decide to go with a time history analysis, just make sure first and foremost, one, that it's worth the investment, and two, that you're properly equipped to handle it. If you don't have a numerical modeling program, it's really not realistic to do time history analysis because, all engineers, especially out on the West Coast, they have numerical modeling programs that are very specific to seismic analysis to help them save on the time that they invest in it because time history analysis is just so prevalent there. So those are the two things to keep in mind. One, make sure that you actually need it, and two, make sure that you're equipped to handle it if you do. Okay, so that's just quiz 3. So I think we can just go to the quiz without a recap. I mean, all the principles are pretty straightforward. So we'll have is just another 5-minute quiz, and then I'll just do a quick case study, and then we'll wrap up. Once again, this is just another 3-question quiz. You'll have up to 5 minutes.
Where do we keep the slow works?
fundamental understanding of why time history analysis is important. But for those of you who work, predominantly in response spectrum analysis and equivalent linear analysis, I hope you're able to sort of understand maybe some of the limitations of response spectrum analysis, but at the same time, you're able to hopefully understand the strengths of it. How it's very efficient to use, how it's sort of widespread, and how it's especially useful for sort of mid-range projects that aren't especially simple but aren't as especially complex as either. So I hope you all found this presentation useful. If you have any questions, feel free to contact me through an email or by phone. What I'll be doing is I'll be posting a recording of this session very shortly. And I understand that for all of you who registered, you'll all be receiving just, I believe, like a USB containing all of the recordings and all the session material. So that way, for future reference, if you want to share it with your colleagues, if you want to review it again, it'll be readily available to you. So once again, this concludes session 5, but next week we'll be going over advantages of utilizing numerical modeling methods for retaining wall design. My colleague Arun, I believe, will be delivering that session. So it'll be the same time next week on the 25th, Wednesday, at 3 p.m. Eastern Standard Time. So once again, thank you for your time and your attendance. Once again, these courses are approved by AIA, so you'll all be receiving professional development hours for this. And once the session concludes, once the final session concludes, I'll make sure to get all of your certifications ready. So thank you again for your time and attendance, and I hope you enjoy the rest of your day. Until next week, thank you again. Goodbye.